Hello everyone, I'm going to explain about this paper high H2O2 production in membrane-free electrolyzer via anodic bubble shielding towards robust rural disinfection. Introduction: this system uses a solar-powered, membrane-free electrolyzer to disinfect surface water. When water passes through the cell, the anode and cathode generate hydrogen peroxide, H2O2. The anode is coated with a hydrophobic porous layer, HPL, which helps gas bubbles escape easily and keeps the electrode surface active. At the cathode, oxygen gets reduced to form H2O2. This H2O2 mixes into the water and kills harmful bacteria. Since the system runs on solar energy and doesn't use a membrane, it's simple, cost-effective, and ideal for rural use. The challenges in the conventional systems: gas bubbles stick to the electrode, blocking active sites and reducing H2O2 production. Yet, some bubble coverage is essential to prevent H2O2 from contacting the electrode, which causes degradation. So this study addresses the trade-off overlooked in previous research by using a hydrophobic porous layer, HPL, that allows for quick bubble escape while protecting H2O2, enhancing both efficiency and stability. Materials used. The electrolyte used is 0.1 molar sodium sulfate, which acts as a supporting medium for the electrochemical reaction. For electrodes, they used a dimensionally stable anode, DSA, coated with ruthenium dioxide and iridium dioxide, and a carbon black-based air cathode. The special innovation in this study is the use of a hydrophobic porous layer, called HPL, created by coating PTFE, which helps reduce bubble accumulation and improves performance. Electrode preparation. Anode, bubble shielding anode. PTFE solution was dispersed in ethyl alcohol using ultrasonication. It was spray-coated onto the DSA electrode and dried at 80 degrees Celsius. Then it was heat-treated at 330 degrees Celsius for 30 minutes in a muffle furnace to form the HPL. Cathode, carbon black air cathode with HPL coating. A mixture of carbon black and PTFE in a 3:1 ratio was sonicate in ethanol. It was spray-coated onto carbon paper and sintered at 330 degrees Celsius. An extra PTFE coating was applied to make the cathode hydrophobic too. Electrolyzer setup and operation. It is a single-chamber, membrane-free electrolyzer, which means no membrane is used. This reduces cost and improves ion flow. Both electrodes are placed in sodium sulfate electrolyte and powered by a DC power supply in galvanostatic mode, with current density between 10 to 50 mA per square centimeter. H2O2 production and monitoring. H2O2 concentration was measured using the potassium titanium oxalate method, which is a colorimetric test. For degradation analysis, they tested different anode potentials, 1.2 volts, 1.8 volts, and 2.4 volts. They also tested cathode potentials of -0.1 volt, -0.6 volt, and -1.1 volts to analyze H2O2 reduction losses. Solar-powered disinfection system. A polycrystalline silicon solar panel was used to power the setup. This shows its real-world application potential using HPL-coated electrodes in remote and rural areas. Reaction selectivity. We want the 2-electron pathway to make H2O2. But if bubbles block the electrode or voltage is too high, the reaction shifts to the 4-electron path and forms water. That's why the HPL layer is important. It helps control bubble behavior and maintain selectivity for H2O2 production. Figure 1. This figure illustrates the impact of hydrophobic layer, HPL, coating on the anode surface in a membrane-free electrolyzer. A and B show the schematic of the system with and without HPL. The HPL, made of PTFE, improves surface properties and enhances bubble release. C, 2, F, show surface morphology. SEM images confirm a smoother surface after coating. Roughness is reduced from 376 to 126 nanometers, which lowers bubble adhesion. G, 2, J, show elemental composition using EDX and XPS. Ru and fluorine are detected, confirming PTFE presence. CF2 and CF3 peaks confirm hydrophobic layer formation. K and L show contact angles. Without HPL, bubble adhesion is high with 137 degrees. With HPL, contact angle is reduced to 40 degrees, allowing easy bubble removal. These results demonstrate that HPL coating significantly enhances hydrophobicity, promoting efficient H2O2 production by reducing bubble trapping at the anode. Figure 2. This figure demonstrates how the HPL-coated anode enhances H2O2 production efficiency compared to a non-coated anode. A shows H2O2 accumulation over time. With HPL, production reaches 5.5 grams per liter in 5 hours. Without HPL, efficiency is much lower. B shows electrochemical impedance spectroscopy. HPL-coated anode has lower charge transfer resistance, meaning better electron flow. C shows linear sweep voltammetry. H2O2 forms efficiently at 1.1 volts versus RHE, which is ideal. Beyond 1.58 volts, water formation dominates, leading to unwanted energy use. HPL controls the current and avoids side reactions. These results confirm that the HPL coating enhances H2O2 production by lowering resistance and improving selectivity, making it a promising solution for sustainable water disinfection. Figure 3. This figure examines the stability of H2O2 bubble formation and electrolysis behavior at different voltages. A, D, G show that H2O2 degrades slower with HPL, which proves better stability. At higher voltages like 2.4 volts, degradation is faster. B, E, H show bubble formation. At 1.2 volts, no bubbles were seen, showing stable operation. At 1.8 and 2.4 volts, HPL-coated anodes created smaller bubbles, improving kinetics. C, F, I show schematics of reactions. Without HPL, bubbles form uncontrollably and block mass transfer. With HPL, bubble size is controlled, improving overall efficiency. These results confirm that HPL coating enhances H2O2 stability while improving bubble behavior, leading to better electrolyzer performance. Figure 4. This figure compares H2O2 stability under different electrode compositions and applied potentials. A shows electrode composition. Carbon paper retains more H2O2 and has minimal catalytic degradation. CB and binder combinations degrade H2O2 faster. B shows current density versus potential. Carbon paper achieves higher current density, meaning better performance. Others stabilize at lower levels. C shows the effect of potential. At -0.1 volts, H2O2 remains stable. At -0.6 and -1.1 volts, H2O2 degrades quickly. HPL-coated anodes retain more H2O2 in all conditions. Overall, the results confirm that both electrode material and applied voltage play a key role in H2O2 stability. CP electrodes minimize degradation, while higher voltages accelerate breakdown. The HPL coating further enhances H2O2 retention, making it a crucial factor in improving long-term performance. Figure 5, Production Rate, Stability, and Prototype. A shows H2O2 production versus current density. From 10 to 40 milliamps per square centimeter, production increases and peaks at around 10 grams per liter. Beyond 40, it stabilizes, meaning further increase won't help due to side reactions. B shows long-term production over 100 hours. With potassium titanyl oxalate, H2O2 remains stable and doesn't degrade, unlike conventional systems. The color change in the solution gray to orange indicates the successful presence of H2O2, confirming its formation and stability. C shows production rate versus current density. At very high current densities like 150 to 200, efficiency drops due to oxygen evolution reactions. Inset plot compares systems and confirms 40 mA as ideal. D. Shows real-world solar disinfection. Contaminated surface water enters a solar-powered unit. The HPL-coated DSA and air cathode generate H2O2. Clean water is collected in a reservoir. No external electricity is needed. E. Shows the full prototype. It includes solar panels, controller, electrolyzer cell, water tanks, and peristaltic pumps. This confirms off-grid capability. F. Shows bacterial disinfection. E. coli colony count starts at 1000. In 30 minutes, it drops to 100. At 60 minutes, below 10. At 120 minutes, it is fully removed. The Petri dish images provide visual confirmation of bacterial elimination, showing how the colonies disappear over time. G. Shows cost comparison. Traditional membrane electrolyzers cost $1,750 per square meter. Membrane-free ones cost only $1,100, making this system more affordable and scalable. Final conclusion. This study demonstrates that a membrane-free electrolyzer can efficiently produce H2O2 for sustainable water disinfection. The system is not only stable and effective but also cost-efficient and scalable, making it a viable solution for global water purification challenges, especially in off-grid and rural communities.